This video is going to have a look at how do we apply a practical application of a geometric sequence to a scenario that involves exponential growth. So the general geometric rule that we use for practical application scenarios is Tn is equal to T1 times by the ratio n minus 1. So T1 being the first term, the starting term, and R being the common ratio, the value that we are multiplying by each time. Now, when we do practical application questions, there may need to be some adjustments to that formula depending on the scenario. We'll have a look at that later on when we have a look at an example. So an important concept with geometric growth is the R value and how do we calculate that R value. And we calculate it by adding on the growth percentage that we are provided with to 100%. So 100% plus the growth percentage. That allows us to come up with a ratio that is going to be increasing the value of the number, because to be increasing, the value of our ratio needs to be above 1. So having a look at an example, if we had a growing at a rate of 5%, our ratio would not be 5% or 0.05. What it would be 100% plus the 5% we are provided with in the question. So that's equal to 105%, which we would then convert into a decimal of 1.05. So if we had a question where we were growing at 5%, our ratio value would be 1.05. Just remembering it does need to be above 1 to ensure that the next number is larger than the number before it. So let's have a look at an example that involves geometric growth. So the population of kangaroos in a national park is increasing by 5% every year. There are currently 2,700 kangaroos in the national park, and we want to write down a rule for the number of kangaroos after n years, and then use that rule in a couple of calculations. So we're going to look at writing the rule, and when we write a geometric rule, we need a couple of values. We need the first value, which we normally call T1, is equal to 2,700. We also need the common ratio, which in this example is increasing by 5%. So it's going to be 100% plus 5%, which is equal to 105%, which is 1.05. So I've got my starting value, which is 2,700, and I've got my R value of 1.05. Now, before I go ahead and write the rule, I just want to take some time to think about what the rule is going to look like. So our current value is 2,700. In 1 year's time, that value is going to increase by 5%, and it's going to be equal to 2,835. Then in another year's time, it's going to increase by 5% and be 2,976. So in 1 year's time, it's 2,835. In 2 years' time, it's 2,976. So we can see that our T1 and T2 values are 2,835, 2,976, but we are actually starting with 2,700. So that 2,700 can't be our T value, but it's actually our T0 value. So our T0 value is going to be 2,700, and that's the value that we are starting with. So that's going to impact on when we come to write our rule, and our rule is going to be Tn is equal to 2,700 times by 1.05, so our starting value times by our ratio, but because it was a T0 value, we don't use n minus 1, we just use n. So the rule that we are going to use in this example is Tn is equal to 2,700 times by 1.05 to the power of n. So now that we have that rule, we can go ahead and have a look at part B and C of the question. So part B of the question is asking us how many kangaroos there will be in 5 years' time. So what we're going to do is we're going to substitute in n is equal to 5 into the equation. So T5 is equal to 2,700 times by 1.05 to the power of 5. Putting that into the calculator, and that equals to 3,445,000.96. So our answer is actually going to be 3,445. So even though it's 0.96, which is very close to going up to 3,446, when t is equal to 5, we actually haven't passed that next kangaroo mark yet. So the population is going to be recorded at 3,445. So, and it's always good to write a statement to confirm what that value is. So the population in 5 years' time is 3,445. So now having a look at part C of the example, and it wants us to calculate how many years does it take for the kangaroo population to double. So what we want to know when the term value is equal to 2,700 times by 2, so 5,400. So I can substitute that into the equation. So 5,400 is equal to 2,700 times by 1.05 to the power of n. So my first step in terms of working out my n value is I'm going to divide both sides by 2,700. So that leaves me with a value of 2 is equal to 1.05 to the power of n. So once I get down to that stage of the calculation, I can go ahead and start substituting in values for n to see when 1.05 to the power of n is equal to 2. So I'm going to start off by substituting when n is equal to 10. So 1.05 to the power of 10, and that's equal to 1.629. So I'm still a little bit away from 2, so I'm going to give 12 a go. So 1.05 to the power of 12 is equal to 1.796. I'm getting a little bit closer, but I'm still a little bit off of 2. So I'm going to skip another 2. So n is equal to 14. 1.05 to the power of 14 is equal to 1.980. So I'm getting really close now. So I'm not going to skip another 2. I'm just going to skip 1. N is equal to 15. So 1.05 to the power of 15 equals 2.079. So I can see now that I've gone past 2. So the point from when I go under 2 to over 2 is during the 15th year. So my answer is going to be in the 15th year. Just remember, in terms of working out, it's really important that we are showing one before and one after as a minimum. So in your working out, you need at least those two lines to show that you have proven the point where it goes over the value that we are looking at. So finishing off with a word statement, it will take 15 years for the kangaroo population to double. So that's an example of how we can apply a geometric sequence to a practical application involving growth.